Hi, I'm Rachael Livermore in Melbourne, Australia, and I'm joined by Jeff Silverman in San Francisco, California.
Hi, everyone. Our guest today is Dr. Brad Tucker of the Australian National University and Mount Stromlo Observatory, and also of many bars that I've hung out with him around the world. And he's going to be telling us today about a project he's working on observing ultraviolet light from balloons. And he's going to explain all the pieces of that statement. Welcome, Brad.
Thank you, and hopefully not pieces of my balloon as it's blown up over someone's land. Because that's a real worry when you put in a flight plan of putting balloons, is what happens when the balloon spontaneously destructs. Like, that phrase is in our flight plan.
Wow, so let's back up a second. Why do you want to put a UV telescope on a balloon?
So the moment a star blows up, you release a burst of X-ray and ultraviolet emission. And so if you could capture this emission, it tells you a lot about the natural state of the star, its mass, its radius, and the energy involved in the explosion. Now, as you know, we appreciate, we can't see ultraviolet light from the ground. So luckily the ozone is blocking the ultraviolet light so we don't get sunburn, especially in Australia where we have holes in the ozone everywhere. And like, I've been burnt outside with a shirt on in the summer in Australia. So this place really doesn't like people to survive. I'm more and more convinced by that. So by seeing this light, you can see these things. We can also look at the atmospheres of exoplanets. So we can look for Rayleigh scattering. So the same reason we get to calculate in physics that UV light and blue light scatters to the ground and red light scatters away because of the composition of our atmosphere, we can detect that around other planetary systems, exoplanets. We can actually even detect cloud systems by looking at ultraviolet light. And more recently, one of my PhD students, Ryan, has shown that you can actually see some types of gravitational wave mergers, potentially even before the merger happens in the ultraviolet. So there's a lot of cool things you can do by looking at this type of wavelength, but we can't see it from the ground. We have to get above the ozone.
So you said that you're flying, 4 to 5 pounds worth of stuff on this balloon. What is that going to consist of? You said, this ultraviolet telescope. How big is the telescope? Is there other stuff on board? What's going to be underneath the balloon?
You have to fit everything you need into a very small payload. So our Pathfinder thing is a very small instrument. It's about this big, and it's actually a wide field spectrograph. So this will break up all of the colors of light. So we know exactly where we stop seeing the ultraviolet color. So we know the moment we can't see any more ultraviolet colors. So modern technologies allowed us to actually 3D print the entire thing in a light plastic thing. So the actual scientific instrument weighs about a pound. So it's just under 500 grams. But then we have to have the parachute. We have to have a communication system. We have this giant reflective aluminum or aluminum, depending on your country, reflective sphere that bounces radar signals off of airplanes if it's passing by. We have a GPS antenna. We have an S-band antenna. We also have a GoPro to capture the images. What else do we have? We have our insulation. We have our waterproof gear. We have our batteries. And we have a backup iPhone. So we have an old iPhone that has a Find Your iPhone feature if we can't find it with the other antennas. I kid you not, it works. It works.
Wow, this is all a lot more hands-on than regular astronomy.
It really is. Like, it's kind of fun because you get to do really fun, simple things, and it's really hands-on, and you have to, do the simple things. So I had my PhD student wrapping something in extra layers of aluminum foil that we bought from the grocery store because we wanted to make it more reflective.
This is a relatively small telescope, right? You said it's yay big, and you're building it from a grocery store. Could you seriously detect exoplanet atmospheres?
With a 30-centimeter telescope, a 12-inch telescope, it doesn't seem big, but you can actually see enough stuff. And there's two reasons we can. One is we're high enough that we're looking at a type of light that we become really sensitive to, but also because we're getting above most of the atmosphere, the blurring and the distortion of the atmosphere becomes way less. So we've actually shown that in a 90-second exposure, we think we can detect this supernova shock wave out to about a magnitude of 19, or roughly hundreds of millions of light years. we should be able to detect the exoplanet atmospheres of things up to 100 light years away with this thing. So if anyone remembers the TRAPPIST-1 system, this was this planetary system that had 6 or 7, depending on what people define as habitable planets. We should be able to measure the atmospheres of each one of those planets.
That's pretty remarkable if you consider that measuring exoplanet atmospheres is one of the science drivers of the James Webb Space Telescope, which is costing how many $billion?
Exactly, that's right. And so far, it's I put it on my credit card.
Okay, so by the time this goes online, you will have already had your test flight. Hopefully it won't have crashed on anyone's house. Where do people go to find out more about it and how it went?
Assuming I'm alive and not in jail, you can go to, right now we're doing everything from the Mount Stromlo Facebook page and Twitter. So if you go to facebook.com/Mount Stromlo, STROMLO, and same on Twitter, we're showing the flights, and we're actually going to be Facebook living the whole flight. And we'll actually, assuming all goes well, be able to transmit some images of real-time space. So you will actually know if the Earth is flat or not. I hope you already know that answer, but we'll be able to show you that answer just in case.
Check the comments below to hear from the flat earthers, I assume, now.
Yeah, that's all right. So, well, maybe I'm part of the conspiracy if it doesn't work.
There we go.
So, it's we will, and this is the great thing about social media and modern technologies. We can now almost broadcast live from near space with cheap and some off-the-shelf equipment. And this is a great thing that science, and especially our field, is moving. Yes, we get to do these big projects, the James Webb, these multi-billion-dollar instruments, but there's also very interesting things that could be done on a smaller scale that can be done with things. Some of these exoplanets are found with just small, almost amateur telescopes you can buy out of the shop. And so science is just so much bigger than any one question that all of them working together provide us with the knowledge of what we want to know. And that is some of the big questions that we've been asking as humans. And we might be getting an answer with stuff I've bought from the grocery store.
All right. Thanks again, Brad, for telling us about your UV telescopes on the bottoms of balloons. I remember you first telling me about this idea a few years back at a conference in North Carolina, and we spent like an hour at a bar trying to come up with a name for this project. So it's good to see it actually launching and hopefully not killing anyone or destroying anything.
No worries. Thanks for having me.
All right. Nice chatting with you.